Welcome everyone. Thank you for joining us for the 27th session in our Gleeble webinar series. Wherever you are around the world, we're glad that you can spend some time with us. My name is Dan Quigley with DSI, and on behalf of our whole team at DSI, we hope that you and your families and colleagues and your communities are staying safe and healthy. Today's presentation will focus on aluminum alloys from processing to service. As always, our goal will be to keep this webinar to 1 hour or less. If you have questions during the presentation, please submit them using the chat feature here in the webinar. Our team will be available to answer some questions directly via the chat, and if time allows, we will have a Q&A following the presentation. Video of this presentation will be available online soon, and certificates will be emailed to you if you are listening to this live. You'll be able to find a link to this video as well as videos of past webinars by going to our website at gleeble.com and then clicking on the resources link in the top navigation bar. Then click on webinars. There you can view past webinars and sign up for future webinars. Next week's session will be presented by Benjamin Adam from Portland State University. And I want to take a minute to thank the team at Portland State, as they've been doing great work with Gleeble for many years. And last year, they graciously hosted the Gleeble community for a user meeting, which was informative and enjoyable. And hopefully we'll be able to gather again in person soon. Today's session will be presented by Professor Cecilia Poletti from the Institute of Materials Science, Joining and Forming at Graz University of Technology. As you know, aluminum alloys can undergo complex processing paths to become high-performance products. Professor Poletti will walk us through some of the research at Graz to study and optimize these complex processes, as well as studies of the materials once in service, including thermo-mechanical testing at the laboratory scale to understand and describe the interrelation of microstructures and loads, and use these findings to design high-performance products. Professor Poletti, thank you for taking the time to present to the Gleeble community, and I'll hand this over to you. Thank you.
Thank you very much, Dan. And I want to thank you first, the people from Gleeble DSI that gave me this opportunity to show you and to share with you what we have done here in Austria. And secondly, I would like to thank all the people that work in this presentation with the results. I'm going to put the laser pointer so you can see them. There are some students, PhD students like René, Aroma, Sarah, Thierry, and some master students like Dinesh, at that time Marta, Peter, and David was a postdoc for very long years, and we have done very nice things together. So I will stop my camera, and you will see only the presentation, and you will hear my voice, hopefully. Good. Good. So the motivation of this presentation is actually to share with you and with the Gleeble community about some experiments about aluminium alloys. Usually people using Gleeble are very focused on steels, and we managed to use the Gleeble also for aluminium alloys. I will show some examples with you, and I will be very happy to have your feedback. So aluminium alloys are almost everywhere, and at our institute we focus mostly on aluminium alloys related to structural materials, so especially for aerospace, automobile industry, going from wrought alloys to cast alloys, so many different type, hardenable, non-hardenable, and so on. So the contents of this presentation is some short overview of aluminium alloys in general, the processing of aluminium alloys, how I see the processing with my eyes sitting on the table. The physical simulations, I will give some examples only from the processing of castings, from hot rolling, cold rolling, hot extrusion, and then last but not least, some examples about during service thermal cycling of additive manufactured materials. And at the end, very, very short summary of what are my thoughts on the topic. So why do we use aluminium alloys? Here, what I'm showing, it's a very classical Ashby diagram. I love them because it's possible to see all the materials together and to compare different type of materials. So here you see the Young modulus as a function of the density. You see all materials, technical ceramics, metallic materials, and so on, which assume only on the metals. And you can see that if I plot the specific stiffness, so which means the Young modulus, the specific Young modulus actually divided the density, most of the structural materials coming from nickel, steels, titanium, aluminium, magnesiums lay on the same line, which means for lightweight design, if I only think about Young modulus divided density, it doesn't matter which material I choose. In the case that I'm producing beams, which means we have a loading beam, then I have to use the square root of the Young modulus divided the density, and there is where aluminium makes a difference with respect to steels and titanium alloys. So it means for requirements on stiffness, for bending structural parts, aluminium alloys are really much lighter than steels and titanium, but not than magnesium alloys. And I would be very happy to hear some more works on magnesium as well. What about the strength? So here what we see is the yield strength as a function of the density, and this is in logarithmic scale. So you can see really the wide range of aluminium alloys, similar but higher than magnesium alloys, close to titanium alloys, of course not reaching these very large values here that only titanium and steel can reach. So we may have to take this into account in the case of buckling, for instance. Okay, so how my eyes look at the processing of aluminium alloys, it's very funny. It's just some lines. And these are lines on the temperature time scale. So this is how I see the processing of casting alloys. We have solidification and cooling from the liquid. And then we may have some homogenization that should bring all the alloying elements into solution and to distribute them properly and more homogeneously. And at the same time, we may have the solution treatment. This could be two separated steps, so we can have one long step of some hours. And during this solution treatment, the very important part is the quenching, so cooling down. This is in the industry not easy, and we have a bunch of different cooling rates in huge parts. And at the end, we may or may have not some aging dependent on the alloy. So if we have aging to promote the precipitation of strengthening phases, then this cooling rate is critical. How do we produce sheets and foils? So again, my simple eye. So after the casting, we have some, so we heat it up in furnaces, and then we have the rolls. During the rolling, of course, the temperature decreases, the speed increases, so we have a strain rate increment and temperature decreases. We may have something here in between of rolling. Then we cool down, we coil it, and we can do again some cold rolling. We may have some recrystallization steps in between to allow further rolling, because due to the strain hardening, we may have some issues in the ductility, so we put some recrystallization steps in between. We deliver in cold rolling or in recrystallize, or for age hardening alloys, we do some solution treatment, and after this aging again. So we can deliver this material here, or after recrystallization, or after aging, or even after solution treatment, depending on the product. And finally, the profiles, the idea is pretty much the same. But instead of having hot rolling or cold rolling, we have the hot extrusion usually in aluminium alloys, where we reach very large deformations due to shear and the combination of shear, compression. So everything is involved there. And then we may or may have not some strengthening by precipitation, which is solution treatment followed by aging. So the first example I want to show is what happens during aging of cast alloys, and not only what happens with respect to the precipitates, but also what happens with, mostly this I will focus to the topic of what happens during relaxation. So what do we have? We have our casting part, which is very complex usually. And this casting part is solidified in the casting die. Then we may do the solid solution as treatment, or the homogenization treatment that I spoke before. And we do the quenching. And the quenching in the industry, as I said, we may have very large temperature gradients, different cooling rates all over the workpiece. And due to these temperature gradients, we form internal stresses. And these internal stresses may, if they are too large, produce some changes in the geometry, even some damage. So usually it's said when we go to aging, which is the last step, these internal stresses are then destroyed, so they don't exist anymore, they are relaxed, and we have a material free of internal stresses. And this was the main motivation of this work. And we studied for this the relaxation of the internal stresses. The lab scale is not that easy, so we thought how to do this. There were many different ways of doing this. We tried many, and we have chosen this. So what we did is we heated up the material to the aging temperature, and then we applied the stress. You may think, okay, but this is not what happens, and you're right. What happens usually is that you have the internal stresses are produced during cooling. So we thought, why we don't first apply the stresses and then heat it up? And the problem is that we observed that during heating up, already the stresses are being relieved. So we wanted to start with a defined stress value and study the relaxation during the time of aging time for a given starting stress value. And then we kept the strain constant. Just remember that the relaxation test, I don't know if you have done such kind of tests, you have to keep the strain constant. And what it happens is that the elastic strain transforms into plastic strain. It's very difficult to think about what is happening inside the material, but this is what we got during relaxation. And we did this with the Gleeble machine that we have, and also with another machine in Politecnico Milano, to compare two different heating rates and heating types. So as you know, the Gleeble is the sample is heated by the ohmic resistivity, and we use a conductive furnace in Politecnico Milano. Now, the two heating rates that we obtain are, of course, very different. So we can reach very high heating rates using the Gleeble machine. So what we got is a bunch of different curves. The differences here are they are not all in the same starting condition. Some materials are in solid solution condition, which are these lines here, the dashed lines. And some others are in an already age condition, so over age or under age and at the peak age condition. But I don't want to go into detail here. So what you can see is that the temperature, at very low temperatures, the stresses cannot be really relaxed as many people thought. And if we increase the temperature, we still have some remaining stresses, and the stresses are not small, so they are really still very large. If we go to very high temperatures, 230 degrees, this is the overaging temperature usually for such a long time. So we are speaking about 5 hours here. So we may have much more relaxation. We also did the normalized stresses, and this is what we got. And these were all the results in Politecnico Milano with lowest heating rates. When we go to the Gleeble, we saw something like this. So let's take a look at the normalized stresses. This is a bit easier. And we can see at the 200 and 180 degrees first some kind of hardening, not every time the same. And for 230, we can't see anything. So at the beginning, we thought this could be a problem when we measure the strain at the Gleeble differently than in the Politecnico Milano. But then we found a pattern for these peaks, and we could see that since we heat up very fast, we may have a correlation of material that is not in the peak aging condition yet, and we have some strengthening. If you compare the Politecnico Milano, these are the red ones with the Gleeble ones, so which are the red ones. We have at the end very nice correlation, but at the beginning they look very different. And this comes because the heating rate is different. If we heat up very slow, we may have all the precipitations happening during heating. It takes up to 1 hour for heating, and this is too long. While if we can heat up very fast, we may see the relaxation, first the strengthening and then the relaxation of the material. And this is very interesting. So we can see that the stresses go up and then down. And this is, if we just take a look at the hardness curves here in 3D, we can see that we need half an hour. Please forget about the quenching rate. Let's take a very fast quenching rate. We need half an hour to reach the peak, which means this is more or less also what we see here, half an hour to reach the peak of precipitation, the strengthening peak. So this was very interesting. We use different machines, and since we have different processes and different heating rates, then we have different processes in our material, in this case the precipitation kinetics, and these produce different relaxation curves. The second thing I want to show is about the classical hot rolling, cold rolling, and heat treatments. We used the Gleeble machine quite a lot for this, and I will explain why these are not other machines. So we have used the classical compression test with cylindrical samples, but also the plane strain. At plane strain, we can better simulate the conditions of during hot rolling. And the most interesting part for us, I hope the people from Gleeble will not be mad at me, is the in-situ cooling. We love it. In-situ cooling for aluminium alloys is really very important, and I will show you why. So we use this sample geometry, and then we carry out finite element simulations. As you know, we have usually a gradient of temperature. This gradient of temperature is reflected as non-homogeneous deformation. The non-homogeneous deformation is usually, you can get rid out of it if you have a homogeneous temperature, if you just control the friction. Even if we can control here the friction, we always have a small gradient of temperature, and we produce this heterogeneous deformation. So we carry out plane strain tests at different temperatures and strain rates to simulate the cold rolling. So these are these curves here. During cold rolling, even if it's cold rolling, we reach, due to very high strain rates, temperatures up to 100 degrees. So it's cold rolling, but after you roll it, you touch it, it's very high if you can. And we use also at the high temperatures to simulate then the hot rolling. We produced a model based on dislocation densities evolution. You can find all what I'm saying in our publications. And we found, of course, a high strain rate dependency at high temperatures, but not at low temperatures. This is what we expected. Of course, at low temperatures, you don't have strain rate sensitivity, or the strain rate sensitivity is very low. This is the most important thing I think that we can achieve when we cool down very fast, and this is that we can freeze the microstructure. The freezing of the microstructure is for the industry not interesting. They cannot achieve this very fast cooling rate. But it's important for us so that we can see what happens in the microstructure. If we leave this microstructure at a given temperature cooling down very slowly, we will have static recrystallization. And then we cannot really understand what happens during hot deformation. So during hot deformation, we have formation of cells of subgrains. And the lower the temperature and the higher the strain rate, the smaller these substructures are. And since we are doing rolling, we are squeezing the grains, and by squeezing the grains, we also may have something called geometric dynamic recrystallization, which means the high angle grain boundaries, the black lines here, meet together and produce new grains. Of course, you need very large deformations for it. So we also saw that particles like MT2SI can have an influence on the dislocation movement, as you can see here. So the interaction of dislocations with particles. And by increasing the temperature, we make the material soften, usually because we increase the movement of dislocations. But additionally, in this case, since we lose or dissolve these black particles here, we also allow dislocations to move even easier, and therefore the materials get even softer at this temperature. So during cold deformation, we have a different situation. We also form some substructure. In this case, they are called cells. And these cells have this structure. So these blue are high angle grain boundaries, and the red ones are low angle grain boundaries. And you can see this type of cells formed all with some orientations. And you can see also that close to some big particles, the aluminium alloys from the industry are, let's say, a bit dirty. They have these iron aluminides, formed iron aluminides with silicon, and they also produce some kind of further strengthening. And you can see close to these black particles, higher deformation zones. This could also have then later an effect on the recrystallization. So we also try to correlate by a very simple measurement, which is the hardness. They always deliver very nice information. We try to see what happens after the cold deformation during heat treatments. And for this, we first have done a hardness map of the cold deformed part. We calculated the strain distribution with finite element simulations, and with these values we also calculated the local stresses using the flow graphs. So this here is shown only the local strain, and we could compare more or less this. I just come back one step again. So these are the local strain here with the local stresses that we implemented with our model in finite element simulations. And with this, we could estimate with the model the subgrain size as a function of the local strain, as well as the dislocation density, since our model is based on dislocation density. Okay, what happens after cold deformation? We use this cold deformation, this stored energy, these dislocations now to produce further structures during further heat treatments. And so what happens again, my very easy lines, the temperature time. So we have our deformation, cold deformation. This is not really a change like this in the temperature, this is just to show deformation. And then we go up, we anneal and see what happens. So we use these hardness maps, which are very easy, and we like them because of it, to characterize the static recrystallization. And as you can see, this is the cold deformed piece, very small sample, and then we heat it up in a furnace. And you may ask why you didn't heat it up in the Gleeble. And I would say because we have seen that recrystallization of cold deformed parts in the Gleeble happens much faster than in the furnace. There are some publications not done by me, but some other colleagues from Lyon, Damien Fabrec is one of them, and a colleague in China did also a publication about it, showing that you can accelerate the recrystallization if you have very large stored energy by electrical transport of energy. It is a very interesting paper from my colleagues. So therefore, we have done this in the furnace. We also did it in the Gleeble, but after this, that what we saw, then we compared and we did it in the furnace. And what you can see is now the softening. So here red are the strain hardening parts, and you can see that the first part that recrystallized, that softened, of course, is the part that had a very large stored energy, very large strain. And here you can see how some parts still remains with the same hardness, probably because we didn't reach the critical strain for recrystallization. So very nice. Pictures deliver the EBSD, of course, and here you can see with the temperature and different holding times what happens. This is not in situ, there are different samples. And what happens after treatments, you can see the very first recrystallized, so they're very small recrystallized grains, and here as well. So this green is a recrystallized grain. You can see the larger the temperature, the smaller the grains are in this case. And this is because we have a lot of nuclease. The nucleation rate is dependent on temperature. So the higher the temperature, the faster the nucleation rate. And then the growth rate is usually much slower. So we just end up with a bunch of very fine grains. We also have seen that at high temperatures, the grain, at low temperatures, so at 300s, the grains that grow very slow and from some nucleations, they grow with a form like this, and this shape is coming from the large precipitates, large aluminates that pin the grain boundary movement. So very nice to see. We managed to put this in the model, and with this we could also get the recrystallization fraction and the grain size that we implemented in finite element simulations. So of course this is only for one sample, but this can be translated into large rolling parts. So you get the recrystallization fraction as a function of holding time and also the grain radius, the grain size. What happens now when we go to very large deformations? Aluminium alloys as well as ferritic steels are materials that usually don't go under the discontinuous dynamic recrystallization as nickel-based or some copper alloys. So already in the 60s, someone asked, do we have any type of dynamic recrystallization in these materials? And the answers came by the hand of McQueen, who said, yes, we have a geometric dynamic recrystallization. As I said, we squeeze the grains. And also later, Godet and Montellier said, we have something called continuous dynamic recrystallization, which is related to the rotation of the lattice. And with this rotation and accumulation of dislocations at the dislocation walls, we increment the misorientation within two different subgrains, and with this we form new grains, new high-angle grain moderates. So how to prove it? This is not that easy, and for this we use the torsion tests. Again, very, very crucial and important compared to other works is to use the in situ quenching to stop any type of static recrystallization and modification of the microstructure. We have that one part rotates, we have the water jets, the sample is positioned here, so this is type of sample that we used. And the sample is also hollowed in one part, like here. So the main idea here is that you get the same section in the middle of the sample as well as in the heads. So with this, you may reduce the gradient of temperature. And I said reduce because it's not gone completely. Still, the gradient of temperature is not that bad. So we may have in aluminium alloys only 5 degrees from the center to the border, which is, I think, very good. In other materials like steels and titanium alloys, we have a bit larger gradient of temperatures. So we did, as always, we test large amount of temperatures and strain rates. And we started with a material, a hot rolled material with very large grains. And this is what we got. And we were really very frustrated because we were waiting for very homogeneous, fine microstructure, and this is what we got. And it's very nice for I don't know, for putting in the living room, but it's very complicated to understand. So we did EBSD of this part, as you can see here, and we have seen that the new grains, the very small recrystallized grains have a very strong texture, so all the same color. Let's put it in these words. We have some grains close to the center of the sample that have much less deformation, and with this you can see the formation of subgrains, so the blue lines are the subgrains. But still we had, and this is taken from the border, so very, very refined grains. So first we proved that indeed there is some refinement of the grains. We also proved that this happens continuously, but we couldn't get very good statistical results. So we changed the material into extruded material that looks in the extrusion direction, like the right picture here. So here you can see in blue the high angle grain boundaries of the as-received materials with very fine grains, and this is the transversal direction. So we said, okay, what happens now if we do torsion here? And if we do torsion here, we got something like this. Okay, so let's come back. We started with this microstructure, we go to 500 degrees, and we increase it a bit, the microstructure. So we didn't refine the grains, and this was very interesting. What is the meaning of this? The meaning of this is that we will get refinement of the grains only at the correct conditions. That means only at the conditions where we produce a substructure that is smaller than the one that we get at the beginning. And this is, as before in the compression tests, dependent on temperature and strain rate. The lower the temperature, the higher the strain rate, the smaller this substructure is. And it takes also longer for the total recrystallization, as you can see here. The black lines, this is almost 100% recrystallized, very nice. And here we still have a lot of substructure. So we also did some measurements of the geometric necessary dislocations. This gives an idea of the percentage of recrystallization, more or less, if I can put this in these words. So in the as-received condition, we have this distribution of dislocations. If we deform at low temperatures, we produce a large amount of substructure. And if we deform at higher temperatures, then we will have much less dislocations, which means much higher amount of recrystallized material. We did the same at the in situ synchrotron. We thought, okay, we bring what we understand into the synchrotron and try to measure the change in the texture and the change in the dislocation density during hot rotation, during hot torsion. And so we have done a lot of data treatment here. I just want to show one of the main results maybe is the evolution of the crystallite size. The crystallite size is not the subgrain size, it's a bit smaller even than the subgrain. And you can see first this decreases and then it increases and then it reaches a steady state. The dislocation density increases and then reaches a steady state. And this is the effective strain is a bit up to 3 more or less. And this is our understanding. So we have starting microstructure that is forming dislocations forms and low angle grain boundaries. And then we form a lot of dislocations, breaking the crystallite size. So the crystallite size, it's smaller. And then we produce, we have a dynamic recovery, and therefore the dislocations are arranged into low angle grain boundaries and the crystallite size increases again. And then it reaches a steady state during continuous dynamic recrystallization. Okay, so the last thing I want to show is about the thermal cycling of additive manufacturing materials. This is not my expertise. We got this material from colleagues of us from Poletti Milano. And again, I put all the processing in my head as before with the temperature. We had the solidification and cooling, which is much faster than in casting alloys. This is maybe the key of the additive manufacturing. We have very fast cooling rates. And it doesn't end up here. After one line, then the second line is coming, producing again a heat treatment locally, and then third line and fourth and so on. So this is not really as simple as this graph is showing. Then they have done homogenization, solution treatment, and aging. You can also avoid this homogenization step, and this is also many times done, and just do the aging step since the cooling rate is very fast. But of course, you have the cooling rate is very fast only of the first layer. Then the other layers are again some heat. This is the material they got. So it's very beautiful. You can see, I don't know if you are used to see casting microstructures. In the casting microstructure of this type of alloys, these are very rich in silicon and copper and magnesium. You have this silicon eutecticum always forming very large shapes, so needles that they are globularized, so very large things. And here, all these needles are in these dark places. So these are very thin, they're very fine, and you produce completely a different microstructure. You can see also some errors, produce some pores and some really big holes. And we took this material and we did what may happen in service. So during service, we have a thermal cycling. We accelerate this. We did it on the Gleeble, this thermal cycling under a given load. We also wanted to do thermal cycling combining with loads. This is possible, but the interpretation of the data was too difficult. So what we did is we took the sample, put the thermocouple on it clearly, and we went into thermal cycling. So the temperature that we set can be seen here. So these are seconds. So you can see how fast the machine reacts. And of course, this is very low temperature, so close to 100. It was very difficult to reach this last temperature. But here you can see how reproducible it is. So it was really beautiful. And we kept the load constant. So I think we kept in this case the force constant, not the load, which I think it's easier. Good, and then we got a signal like this, stroke. Okay, looks very strange. And we also got the L gauge, which looks nicer. And with this signal, the L gauge, we extract. We got two. The total signal is the total strain is this black here. But we were interested only in the inelastic strain, which means we had to extract the thermal expansion out of it. And this sounds trivial at the beginning, but it was not. And after we did this, then we got the inelastic strain. So as we can see here. And the curves looks a bit like a creep curve, but instead of, so all this, what you see here in red, you have to imagine had the shape of a triangle, yeah? So going up and down with temperature. We got this an inelastic strain as a function of number of cycles. And of course, the higher the stresses are, the lower the number of cycles. You reach up to a tertiary creep, some kind of tertiary creep. And then we measure the number of cycles to failure as a function of the stresses. So you can see the higher the stresses, the lower the number of cycles the material resists. And these were ongoing, so this didn't break. And we also relate this damage to the plastic strain. So we could see that at very low stresses, the plastic strain is very small until we reach a peak, and there is where our material breaks. And here there are some lines where you can see close to the fracture. You can see that the material fails there where we have a large amount of heterogeneities. So of course, these kind of materials are not easy to test because they are very heterogeneous. But even though we could see that we could simulate this testing, this thermal cycling, and got some information out of it. To sum up, I want to just give my thoughts on all what measurement, so thermomechanical measurement means. So we do laboratory experiments to simplify the industrial process. We get information we cannot do large parts, and this is not the idea. We make like a puzzle. We just get local information of these large parts. For this, we make our matrix of experiments. So it means we need the information of the industrial processes to do this. We use the laboratory experiments also to separate physical phenomena. And this is not the simulation of the process. So sometimes we quench very fast and we cool down very fast, or we go to very large deformations. This is for the industry itself not interesting. We cannot go that fast in the cooling rate. But this is important for understanding what happens at every single step with the material. What happens during the formation, what happens during cooling, what happens during. So we can really separate all these physical phenomena. And sometimes we can't. But this is why we do the laboratory experiments. We use different machines and different devices, and all different bring. We need the combination. We need the combination of machines that can do very fast heating rates or cooling rates, but also we need machines that do not modify the material by electrical currents or by temperature gradients. So we need the combination of all the machines. We need to combine methods, metallurgy, microscopy, XRD, TSE. So we need to combine methods to understand how the material behaves. And some of these methods are in situ, like synchrotron, but also scanning calorimetry or dilatometry. And some are just post-mortem, like metallography. There are, of course, some metallography that can be done in situ as well. We need to do a critical analysis of the data and of the method and compare and try to understand why we got what we got. And then we can use not only what we measured, but also what we understood from the experiments into models and simulation. What we cannot understand from the physical phenomena, we cannot model, and this is clear. And then we can use the models and simulations to predict, to interpolate, to describe heterogeneities, and so on. So with this, I would like to finish. I want to thank you for your attention. Thank all the guys that have been working. So I put the faces only of the guys that were mostly involved in this all experiments, and also thanks for the supporting agencies for doing this research. Okay. I hope you enjoyed, and I'm open for your questions.
Great, thank you, Cecilia. This was a great presentation, and I think, as you noted, I think there's some very nice images there as well. So you may have a career in the art world as well. There's some great close-ups of some of your experiments. So great work. We do have a few questions. Let's see here. If we can go to slide 9, there's a question. It says, is the heat treatment between two cold rolling stages intentional, or is it just adiabatic heating due to the cold rolling?
The cold rolling, okay, this is the other one, okay. So this can be done or not. Usually when we do cold rolling at the industry, you start getting material that becomes very brittle and not deformable because of the strain hardening. So the amount of dislocation is such large that we cannot deform it further. So there are in some processes a step that is called, this here is called the recrystallization step. And with this, we make a thin layer, as thin as possible. We do the recrystallization step. We recover the ductility of the material. We lose the strain hardening of the material. And with this, we can go on further making thinner foils. So this is intentionally when it's done, of course.
Okay, great, thank you. I believe the next question related to slide 14, or around 14. The question is, how is elastic strain transformed into plastic strain? Is it an elastoplastic deformation strain rate dependent?
Yes, it is. It is. It's we have done, so I didn't show here the calculations of the plastic strain rate and how does it transform. So what we got is we have the formation of dislocations at the very first beginning, and these dislocations annihilate during the aging. These dislocations are not formed everywhere. That's why people says, okay, but you have done the relaxation test going into elastic strain. You're right. The elastic strain is only the macro elastic strain. If we go locally, since we have a multi-phase material with silicon particles that cannot deform and some copper particles that cannot deform, the only thing that we deform is the aluminium matrix. And the aluminium matrix will not homogeneously deform. It will deform very strongly close to the silicon particles, probably producing some plastic deformation there, local plastic deformation there as well, and some dislocations. So it is elastic in the macro, it is not elastic completely. And how it's transformed into plastic, again, so we have this movement of dislocations that will allow the plastic deformation over the time. It's a very small deformation, of course. It's not a huge plastic deformation. It's very small, but still is there.
Great, thank you. The next question is on slide 17. It says, during stress relaxation at 230 degrees, have you studied the microstructural behavior like dynamic recrystallization and grain growth?
At these temperatures, we don't have dynamic recrystallization. In aluminiums, we don't have dynamic recrystallization. We have only continuous dynamic recrystallization. We don't have grain growth, of course. This is everything dynamic. And especially at these very, very low temperatures, we may have some recovery. And this is exactly what's happening. We are studying this microstructure, so we have done EBSD of all these things here. But the most important is remember that this is not only a relaxation of a pure aluminium, it's a relaxation and aging. So we also spent a lot of time studying the precipitation, the precipitates formed here with TM. So we have done in parallel TM and EBSD. And we also have seen dislocations in the material after quenching, which was very, very surprising.
Okay, great. So a couple of questions left here. I believe this question was around slide 27. It says, how does the inhomogeneous temperature distribution between front to back affect the results in PSC samples when looking at the strain distribution and recrystallization?
Yeah, okay, so we have the strain distribution here. This was cold deformation, so here we don't have a temperature distribution. And so here what we have is a strain distribution due to friction. And it took a very long time to see which friction factors we should use here. We adjust the friction factors. We are not experts in friction coefficients. So we adjust the friction factors just to get the same shape of strain that we got with the hardness map. So we know that if we increase more the friction factors, we will have different shapes. We may have only one cross or two crosses or no cross at all if we have homogeneous deformation. But this is everything cold. Then when we increase the temperature, we do it in a furnace. So there is also no temperature distribution here. What we have is a homogeneous recrystallization grade, so not visible here because it's over the time. It's homogeneous, heterogeneous, sorry. And also grain size due to the stored energy here. So due to the deformation here, actually. If we deform more, we get finer grains. So this is, there is no temperature gradient in this specific slide. There's only a strain gradient due to friction and grain size distribution due to different local strains.
Okay, great. And I think we have time for one last question here. It says, do you find that generally porosity and voids are more prevalent in additive manufacturing?
That voids are what? Sorry, I didn't hear
I'm
you.
sorry, that voids, porosity and voids are more prevalent. They occur more in additive manufacturing.
At the moment, yes.
Okay.
But I think it's it's a very new, and not very new for all the materials, but it's a relatively new process compared to casting. If you compare also sand casting, gravity sand casting, you may also have a lot of pores in the casting process. But if you compare with squeeze casting, so very high technologies in casting, you get rid of pores. And I think we are in additive manufacturing also the position where we have to improve all the process. It's some people already managed to do this on some materials, but this is still in process of improvement. At the moment, there are still a lot of pores. There are a lot of issues with toughness due to heterogeneous distribution of phases. But as I said, you also have microstructures that you don't get with casting. You have very fine distribution of phases, and we may get columnar grains. So it's very fascinating work.
Great. Very good. Well, this has been great. We do appreciate you taking the time to create the presentation and share with us here. So thank you very much.
Thank you, and have a nice day.
Yes, thank you. And if anybody has any questions for Professor Poletti, if you'd like to reach out to me, I can connect you. There are a couple of questions we didn't get to. We will pass those along to Professor Poletti. But if you do want to reach out directly, let me know and I can connect you. If anyone has any technical questions about the operation of the Gleeble, please contact our service team. I mention this on every webinar, but we do have a new customer support portal, which you can access on our website on the resources tab. And there you can, if you're a Gleeble user, you can create an account, and then you can search a knowledge base as well as create support tickets. That is the best way to get support. If anybody has any questions about how Gleeble can support their research, please email me or anyone on our team, and we'll connect you with an expert in your area. Again, thank you everyone for joining us, and we do hope that everybody stays safe and healthy. Have a great day.